Welcome back. I'm very happy to introduce the first speaker of the last session today. It's Shruti Paranjape, and she'll talk about hidden zeros and the double copy. Go ahead.
Um, Excellent. Okay. So welcome to the last session. So I today wanted to talk about hidden amplitude zeros and the double copy. But before I do that, I wanted to thank the organizers for the opportunity to tell you guys about this stuff. The talk will mainly be based on this paper that came out in March with collaborators Yaroslav Trinka and Carol Kampf and three of their students, Christoph Bach, Taro Brown, and Umut Oktem, all of whom are going to be on the postdoc job market at the end of the year. So look out for that. So the talk itself is going to be, I think, reasonably simple and easy to understand. So yeah, I encourage you to sort of stay with me through all the steps so that we can have interesting discussion towards the end of this. Okay, so the playground is tree-level amplitudes, nothing complicated, and tree-level amplitudes are famously rational functions. And rational functions, even more famously, take the form numerator divided by denominator. Now, we've seen in QFT 101 that the denominator of an amplitude, a lot is known about this denominator just from locality, you know, where the poles are, and those poles correspond to whatever the spectrum of your QFT is. In addition, there's also unitarity. So unitarity tells you something about the numerator of this rational function, but of course, it doesn't tell you everything. It only tells you about the numerator at some singular kinematic point, right? So what unitarity doesn't tell you is what is happening to this numerator off of the pole. So what are these off-pole or contact contributions? Okay. Now, any rational function, you know that as long as I know where all the zeros and all the poles of this function are, I know exactly what the function is. And we've spent some time in the amplitudes community thinking about zeros. Maybe the most famous example is soft zeros. So zeros of an amplitude that comes from a theory of spontaneous symmetry breaking. And when you have spontaneous symmetry breaking, you automatically have some kind of soft behavior or enhanced soft behavior. So the soft bootstrap is a program that then tells you that the only theory you can write down with three amplitudes that behave in this way are these three theories over here. And we'll see two of them quite a bit in this talk, the nonlinear sigma model of pions and special Galilean theory. But if you're not familiar with these, that's fine. They're fully determined by this behavior, soft behavior. Okay, so those are famous zeros. There's the zeros that we'll talk about today are slightly different. They're a little more similar to radiation zeros that have been discussed in the past, for example, in this paper over here. And these are zeros that, for example, at 4 point in a process like this, happen at a very specific angle. Okay, so the tree-level amplitude vanishes, and so you see some kind of dip. So it's more similar to that than Adler, but if it helps you to think about an Adler zero, go ahead. All right, so what are these hidden zeros? So these were discovered or discussed in this paper over here by Nima Arkani Hamed, Chu Kao, Zhendong, Carolina, who will tell us more about a lot of things tomorrow, and Sang He. Okay, and so these are points in kinematic space where the amplitude vanishes in a particular set of theories, Yang-Mills, nonlinear sigma model, trace phi cubed, and Yang-Mills coupled to a scalar, or Yang-Mills scalar for short. All right, so what do these look like? So at 4 point, it's very simple. I'm just sending t to 0, and the amplitude vanishes. Okay, so I should mention a few things before I say this. These conditions I've written down over here are the zero conditions for a d-dimensional scalar theory. Okay, so for this, all my amplitudes are just functions of Mandelstam invariance. And so when I send t to 0, the 4 point amplitude vanishes. At 5 point, when I send S13 and S14 simultaneously to 0, the amplitude vanishes. And at 6 point, I now have two different types, one where I send these 3 Mandelstamms to 0, and one where I send these 4 Mandelstamms to 0. Okay. So these are just points in kinematic space where the amplitudes of these theories happen to vanish. I just want to point out that this is not actually the Adler zero, even though it looks like it. It's 1 Mandelstam away from being the Adler zero. Okay. Okay, so let's look at an example. Trace phi cubed, very benign, 4-point. You have these 3 contributions. Because I'm looking at an ordered amplitude, this one doesn't contribute, which means this is the amplitude. I sum these together, get something in the numerator. It happens to be t, so it vanishes when t goes to 0. Straightforward. But one thing to notice over here is that these zeros don't actually require both pole terms, otherwise they wouldn't exist. So for example, in bijoint scalar, this wouldn't be a 0. Okay, another side. Also very easy to see. Literally, the 4-point amplitude is t, so when t goes to 0, the amplitude goes to 0. At 6-point, things are less manifest, so you have these pole terms over here, and you have a contact term. You write them all down, and then you look for where the zeros exist. So I remind you, the first one is S131415 goes to 0. On that kinematics, this is what the amplitude looks like. You can show that it vanishes. Similarly, for the other one, some things go to 0, some pole terms change, and the amplitude vanishes. But it's not manifest, and it requires all pole contributions. Okay, so good. At n point, there are n over 2 number of these, or floor of n over 2 number of these zeros. And one convenient way, which is discussed in this paper, to read off these conditions is from the kinematic mesh that some of you might recognize from one of Nima's talks at Amplitudes maybe a couple of years ago. Okay, so basically in this kinematic mesh, every closed rectangular region corresponds to a 0 condition. Okay, and these are the generic form of the 0 conditions. All right, so these are the rectangular regions. And in addition to there actually being zeros, the amplitudes in these theories have an interesting property, which is that they split or they factorize near these zeros. So if I chose one of the Mandelstamms to not send to 0, so let's say I choose this one in the middle as non-zero and send the rest to 0, then my kinematics splits in the following way, where I get this side of a kinematic mesh times that side of a kinematic mesh, and my amplitude then looks like a subamplitude, another subamplitude, and then this prefactor over here. Okay, the prefactor, if you can't tell already by looking at it, is just some trace phi cubed 4-point amplitude. It's a simple prefactor. In the case of scalars, it's more complicated for Yang-Mills, but you can still predict how the splitting is going to take place. Okay, good. So I just want to emphasize that unlike near poles, there is no physical reason why this factorization should take place. There are, of course, formulae that make it more or less obvious that such a property will be satisfied, but there is no physical reason as to why. There's no symmetry principle that's telling you that the zeros should exist, nor that the amplitude should factorize near these zeros. Okay, so just a little bit about what happens when you also have polarization vectors. So when you have polarization vectors, then every time your 0 condition includes Sij equals 0, I also need to send epsilon I dot pj, pi dot epsilon j, and epsilon I dot epsilon j to 0, where epsilon is the polarization vector. Okay, so it's easy to see that Yang-Mills, for example, the contact term goes to 0, and then the pole terms go to 0 on such a condition at 4-point, let's say. Okay, good. So this is the list of theories that were first discussed. And so this is where the hidden zeros were first found. And anyone who sort of lives and breathes the double copy knows that all of these are related to the double copy in some way. Okay, good. So I didn't anticipate this, but I'm actually the first person to talk about the double copy at this conference. So anyway, we'll figure it out as we go along. This is a web of theories, and okay, so one thinks of the double copy as a map on the space of theories. You say that theory A times theory B gives you theory C at the level of the amplitudes. So for example, if I'm looking at Born-Infeld theory, the amplitudes in Born-Infeld theory are given by the KLT formula between Yang-Mills and nonlinear sigma model. Okay, and then many other examples, and this review is very useful and will tell you everything you need to know about the double copy. One exception to the list of theories is trace phi cubed. Okay, so trace phi cubed doesn't actually participate in the double copy, but the amplitudes are identical to the diagonal amplitudes in bijoint scalar theory. And bijoint scalar theory does participate in the double copy. Okay, so all this to say, all of the amplitudes with hidden zeros seem to have something to do with this double copy map. So just for those of you who are uninitiated, for a theory to be a single copy, it needs to satisfy the BCJ relations. And for a theory to be a double copy, its amplitudes have to come out of the KLT formula. Okay. Okay, good. So this is roughly what I want to talk about. Do the BCJ relations mean you have to have a hidden zero? Do the KLT relations mean you have to have a hidden zero? What are the relative strengths? So in the sense of constructing an effective field theory with these properties, what are the relative strengths of these properties? And then finally, what about factorization? And there's a lot of very recent exciting papers on point number 4. But okay, let's start with the first point. All right. So this is a very carefully chosen basis for the BCJ relation at 6 point. And you'll see in the corner over here a color and a kinematic zero. But anyway, so all right. So on the first zero condition, you can see that every single prefactor in front of these amplitudes vanishes. Okay. On the second zero, you can see that every single prefactor in front of these amplitudes vanishes. So without thinking about what these actual 6-point amplitudes are, you can see that this amplitude on the left-hand side has to vanish in these limits, right? All right. Sorry, so I should say that only happens as long as there are no poles at these positions in these amplitudes, right? So if there are 2 particle poles, then this argument falls through. We'll talk about that in a second. But before that, let's talk about trace phi cubed. So now if I have 2 orderings, I just add an ordering to my amplitudes. And then again, you'll see over here that none of these amplitudes can have 2 particle poles because of the second ordering. They're not compatible with the second ordering, which means that I've written trace phi cubed as a sum over bijoint scalar. These guys don't have 2 particle poles, which means this amplitude over here inherits all of these hidden zeros because it satisfies the BCJ relation. Okay, so all the things that satisfy the BCJ relations, as long as you evade 2 particle poles, has to have these zeros. So NLSM, only 4 particle interactions. Trace phi cube we just discussed. Yang-Mills is an interesting case because though it has these 2 particle poles, it needs to look like a 3-point amplitude times a lower point amplitude on the 2 particle pole. And the 3-point amplitude happily actually vanishes on this condition because of these epsilon dot products. Okay. Similarly, you can check that other theories people might be interested in, like df squared and f cubed, plus their high derivative corrections, all satisfy the BCJ relations, avoid the 2 particle poles, and so have to have these hidden zeros. Okay. So just quickly at endpoint, one can use this representation to show that one of the terms in this product has to vanish. And so you can show definitively at endpoint that this statement is true, that BCJ relation plus absence of 2 particle poles gives you hidden zeros. Okay. All right. So let's now discuss whether one can use this as a way to construct an effective field theory. So a lot of people have been constructing these high derivative corrections that are compatible with BCJ for some time now. And the construction is quite simple. You're trying to look for all possible local 6-point amplitudes with some particular mass dimension given over here that satisfies some constraint. In the case of the Adler zero, this one over here is the statement that the soft bootstrap works. It's interesting that there's also only one thing you can write down with the hidden zeros and only one thing that satisfies BCJ. All right, leading order accident, you can see that things change immediately after, but all of these follow this pattern over here. So it's much easier to have an Adler zero than it is to be BCJ satisfied. Okay. Good. So it's also interesting that Adler doesn't actually equal to the hidden zero, but in 4 dimensions, that is true because of the Gram determinant. So remember then that we are in D dimensions when I make these statements. All right. Do these zeros double copy? So in a very similar vein as the BCJ argument, I just write down the 6-point KLT relation. Okay. And again, I choose my basis somewhat carefully. And here, because of my poor LaTeX skills, you only see the last row of the matrix. But that's enough really to make the point, which is that on the first zero, this vanishes fully. And actually, you can show that the whole KLT kernel vanishes on the support of this zero. So good. So that means that M6 will inherit this zero, again, as long as there are no 2 particle poles. Okay. You'll see over here that this row actually doesn't vanish on the second zero, and that's because I chose a bad basis. So for any zero, I can choose some basis for my KLT kernel so that this formula vanishes, which means, and then the BCJ relations tell you that this choice of basis doesn't actually matter to the construction of M6, which is basically to say that any M in the double copy inherits these hidden zeros. So an example is the scalar theory, special Galilean, that is the double copy of nonlinear sigma model with itself. And so again, 4-point is somewhat trivial, 6-point is not manifest, but you can still show that these are indeed zeros and they're inherited by the double copy theory. In addition, you can also show that these amplitudes constructed in such a way factorize near these zeros in exactly the way that you would expect, despite the fact that this kinematic mesh is a very ordered object, and this amplitude is fully permutation invariant. Okay. Okay, so again, endpoint formulae are available. You have to do a careful analysis, but then you can show that if I write the KLT formula in this basis, then the mth type of zero is manifest, and then you can show that if there are no 2 particle poles, that you have hidden zeros. Okay, good. Again, I can do a sort of bootstrap analysis or an EFT analysis of what kinds of things I'm even allowed to write down. And yeah, so here I had a hope that was dashed, which is the following. So when it comes to what you're allowed to put into the double copy, you know that you need to satisfy the BCJ relations. When you look at a double copy theory EFT, there's no way of telling which terms came from the KLT relation and which ones didn't, right? So one thing you might hope is that an extra condition like this hidden zero condition would identically land you on the terms that are generated from KLT. And as you can see, this worked very well in these pink entries over here, but at p to the 18 or mass dimension 18, I have one term that's different. Okay, so this is not an identical condition, and again, KLT generated terms are much less than hidden zeros, less than enhanced soft behavior. Okay, I will say that this doesn't include the requirement that these amplitudes factorize correctly near the zeros. And so one possible thing to check would be whether adding factorization to your bootstrap actually changes this result in any way. Okay, all right. So in the last bit, I will, I will talk about factorization. In particular, what happens to factorization when you're thinking about these amplitudes genuinely in an effective field theory way. Okay, so you remember that the prefactor when you looked at the factorization rule looked like this. Now, if I add higher derivative corrections, what happens is that I now not only get lower point higher derivative amplitudes, I also get this prefactor, which is now corrected with higher derivatives. So this prefactor that's been corrected with higher derivatives can be identified as a trace phi cubed amplitude with high derivative corrections, but you'll notice this is not all possible. Like this 7 should already really concern you a little bit, right? So these are not generic high derivative corrections. And anyone who sees this and figures out what is special about these particular ones, please come talk to me later. But for now, it is this, and you can check that it's the same prefactor no matter what high derivative corrections I've added to my theory. And this also works for the single copy. It's always this particular set of corrections. Okay. So what that means is that I'm not going to be able to read off factorization directly from a BCJ relation or a KLT relation. I'll have to use a formalism for the double copy that actually differentiates between stuff in the leading order and stuff which is high derivative. And one thing that does that is the CHY formula, right? So if I use the CHY formula, you can show that the CHY integrand, for example, for special Galilean, factorizes. So do the scattering equations. And there was a paper last week by Kao, Dang, He, Shi, and Zhu, who discussed this at great length. And they talk about exactly how on these split kinematics, the scattering equations and CHY integrands split. Okay? And in some sense, already, this is telling you that that had to happen because you can't have the same splitting rule at leading order and at high derivative order. Okay, so I just want to end by talking about how things work when you now add spin. So for a theory like Born-Infeld, everything goes through and you can satisfy these polarization, as long as you can satisfy these polarization conditions, you won't get any two-particle poles. Gravity, on the other hand, requires that your polarization tensor has the split form over here. So you can think about this as a split polarization or a factorized polarization. Or you can think about it as some like polarization for a fat graviton. So the graviton that comes out of a Yang-Mills times Yang-Mills double copy. Okay, so similar conditions are true when you're looking at df squared times df squared or even higher derivative Yang-Mills. You still have these polarization conditions, so you can only see the zero as long as these polarization conditions are satisfied, which basically boils down to this condition on the polarization tensor. Okay, so I think that there's a lot more that one can think about. In particular, what happens in 4 dimensions. So one thing about the polarization tensor property is that it's always true in 4 dimensions. So in 4 dimensions, the number of graviton polarizations are the same as the number of gluon polarizations. And they all take this form over here. So thinking about what happens to these zeros in 4 dimensions is interesting. This is something I'm thinking about with Callum Jones. And what we find is that it's intimately related to the BCFW expansion for Yang-Mills. Right. Another thing is whether or not one can use these zero constraints recursively to build amplitudes. So in some sense, all that goes into BCFW is location of poles and factorization near poles. So now that we have location of zeros and factorization near zeros, it's a natural question to ask whether you can somehow use that to recursively build amplitudes, especially in high derivative theories. Good. So let me summarize. We saw in this talk that there are a certain class of theories that have these hidden zeros, which are just kinematic points where the amplitude vanishes. We saw that any theory that satisfies color kinematic duality has to have these zeros. In addition, we saw that anything that results from the double copy also inherits these hidden zeros. And finally, we discussed how higher derivative or effective field theory amplitudes factorize near these zeros and give you a very particular correction to trace phi cubed. So yeah, with that, let me thank you for your attention.
Thank you. Questions?
Well, I have a few questions. So one thing that we also saw in the case of the NLSM, these factorizations near zero sometimes produce these mixed amplitudes where there were also scalars on top of pions. So is there something similar for these? I mean, you do the special Galileans by double copying the NLSM.
Mm-hmm.
And in terms of also the sort of higher order corrections, do you see any of these features?
Yeah, so when you do this, right, over here, you could instead do what Carolina is saying, and you could look at factorization not into even times even, but odd times odd. And in which case you get these mixed amplitudes. So if, say this was not a super special Galilean, this was NLSM instead, then you get NLSM plus phi cubed. And so literally just the double copy of that plus higher derivatives is what you'd get on this side. So everything just continues to be true. The only thing you have to be careful about is you'd have to add contact interactions between the pions and the phi in your EFT. So you have to genuinely do EFT in pions plus phi. But it all goes through other than that, yeah.
Yeah.
Thank you for this great talk. Do you think that you can get some understanding about improved UV behavior from these hidden zeros?
So good question. So I think, so at least what we're looking at now with Callum is looking at what happens to the BCFW terms in 4 dimensions for Yang mills. Now BCFW obviously is very closely related to UV behavior. And we find that term by term in the BCFW expansion stuff is vanishing. So that's kind of, I don't want to say too much more than that because it's still quite preliminary. But the fact that that is true, that term by term in both Yang mills and gravity, these things are going to zero, makes me think that there is some connection between the two. But that's the level at which we.
Well, there was this paper by Laurentio this week that actually showed that that's true for
Okay, so
like the NLSM, not for gravitons still. Yeah.
Mm.
Just one last question. Oh, is there any question? I'm so sorry. This is my first time doing this. Oh, there it is.
Hi, Shruti.
I don't know.
The KLT kernel is the inverse of the Boyajian S matrix. So is there a relation between these zeros and factorization channels of the Boyajian scalar?
Nominally, yes. I mean, like you said, the KLT kernel is the inverse of the biojoint matrix, but that I think so. When you I have to go too far back, but when you take an inverse, you're kind of, there are a lot of things that are happening. For example, there's a 1 over the determinant, and so some of the zeros in the KLT kernel seem to come from the 1 over the determinant, and some of them seem to come from like just the fact that you're taking this adjoint matrix. And that depends on which basis you've chosen. So it's possible that this is true, but it's definitely not as simple as you've gone onto some factorization channel in biojoint scalar, and that looks like a 0 in the KLT kernel. So it's not as straightforward as that, but maybe there's some underlying connection that we haven't seen yet.
Thanks.
Yeah.
Okay, do you want to ask a question?
Oh, just quick. So can you understand the factorization near zeros from the double copy or no?
Well, so this paper last week by Song and his collaborators, they use the CHY formula to show that the splitting happens, and in some sense, the CHY formula is leading order double copy.
Okay, at leading order.
Yeah.
Okay, then let's thank Shruti again.